Yeah, we'll see. If the Zoom people come in later, then that's fine. Either way, I'll have a recording of this as usual. Okay, so today we're going to start talking about propositional logic, which essentially is the kind of starting point to how we should be thinking about math. So the idea is like, you know, when we talk about math, when we talk about like learning math and talking about math, well, I tricked you. This isn't a math class, it's an English class, right? Like we're here to learn grammar essentially. So it's an English class in disguise that I tricked you all into taking a math class, but it's not. Because we need grammar, right? Like if we want to speak a language, we need to learn grammar, we need to learn the vocab, and that's what math is. Math is a language, and we need to learn to use the vocab, which will come later. But before we even talk about the vocab, you need to know how the language works. And math is, like I said, just a language. So let's kind of start with what we need in grammar, right? So the first thing is a statement, right? That's kind of the first thing we start with. If I'm talking to you, I can't just talk in broken sentences. I have to use full statements, and that's what we kind of start with in math. Some of this stuff, I'm going to kind of give you a breakdown. Typically, if there's a word, if I underline it, that's typically a definition you should know. I might give other definitions that it's good to know, but if I don't underline it, it means, yeah, keep it in your mind, but it's not too terribly important if you do or don't remember what it means. So statements can be atomic or molecular, and this kind of gives you the idea of, you know, whether it stands on its own or whether it's a bunch of statements put together. And sometimes it might be hard to figure out, so like with more complicated statements, sometimes it's hard to figure out if something is atomic or molecular until you actually like sit down and look at it, right? It's one of these things that if you sit down and actually think about what your statements are, it's really obvious. Like if I talk to someone who doesn't know math at all and say, hey, the moon is blue and round or something like that, people say, oh, that's a sentence. But I could easily say, well, technically I can split that into the moon is round and the moon is blue, and those are both separate statements, right? So that kind of gives you an example for what should a statement be, right? A statement should be something that stands alone. Right, so just that and nothing else has a meaning, and more importantly, as true false. So a statement should be anything that I can claim is true or false, right? So you know, obvious examples, you have stuff like, you know, the sky is blue, right? Say I have something like I have 5 minutes, which obviously isn't true, but would still be a statement, right? When we talk about statements, we don't care if it is true or false, just whether or not it can have true or false assigned to it, right? Now, turning this into kind of like math examples, you know, something like 2 plus 3 equals 7. That's a statement. Again, it doesn't matter if it's right or wrong. It's just something like that. Now, what about something like 2 plus 3? Well, obviously, this isn't a statement, right? There's no true and false about it. We can compute it, but that's a completely different thing, right? For now, one thing I'm going to note is that because notice how far back we're starting, right? Obviously, we all know what statements are. We all know what sentences are, but it's almost kind of stupid to start defining things this far back. So the idea is that we're going to just go as far back as we can and basically forget that we know anything, right? So imagine, and I'm going to be really strict on talking about mathematical objects. And this is something I'm going to be stressing throughout the entire course, is when we're talking about mathematics or you're trying to read a piece of mathematics, everything you run into is an object, right? If you're reading a sentence, well, the sentence is a statement, or the sentence is a formula, right? We have names for all of these objects, and each of these names have a definition that tells you how you should be thinking of this, right? So we might not know what plus means, right? You all know what 2 plus 3 is, but question is, do you really, right? We might not have defined what it means to add things. You might not even know what 2 and 3 are, right? For now, we're just gonna assume we know what the numbers are, right? Let's just assume that any real number, if I say like pi or 3.4 or 1, let's assume that we know what those are, right? In a later section, I'll talk about why we don't just know immediately that those exist. If we start from nothing, the only thing we have is nothing, right? And that's what we're talking about in set theory. But for now, let's assume we have stuff like that, so we don't have to, go too far into the rabbit hole. So if I give you something like 2 plus 3, even assuming you know what 2, 3, and plus are, even if you know what all these symbols mean, that's still not a statement, right? It's not a statement because we can't assign this a true or false value, right? Now, let's see. So given that, is this a statement? X plus 7 equals 9. What do you guys think? Exactly. Right now, so this is where I'm starting to be really specific. I told you guys that we're allowed to know what numbers are, right? I told you that we're allowed to know, hey, what does 2 mean? What does 3 mean? There's some construction that we're kind of ignoring, but there's some construction that tells us what this is. So, like you said, we know what 7 is, we know what 9 is, we even know what this equal signs means. We don't know what X is, right? We know, in our terms that we've learned in like high school and stuff like that, we know X is called a variable, but let's just say we don't know that yet, right? We won't call it a variable for now, but we don't know what it is. X could be a fixed constant, X could be unknown, but either way, we have no idea what this is. So this is actually not a statement. And this is kind of one of the harder things to look at in logic, is it might seem obvious at first whether or not something is a statement, but at the end of the day, it really does force you to understand what you do know and what you don't know, right? So this brings me to the biggest point that I always make, and you hear me repeating, this is one of the few things that I'll be repeating a lot throughout the course, is you're only allowed to know the things I told you you're allowed to know. And this is really hard for a lot of people because we've learned stuff about algebra, we've learned stuff about geometry, we've learned all this stuff in previous classes that we're like, oh, I know 2 plus 3 is 5. I know that this formula works a certain way and such. But if we really want to build math from the ground up, you don't know anything until you've been told what the definition is. You can't really make up definitions on your own, right? You can't just say, hey, I'm going to define this way, and we're going to go with that. Well, you can, but then all of math might change based on your definition, right? So if we want to go down the rabbit hole, what happens when you want to define something a certain way? So for example, if we talk about the natural numbers, there's kind of this argument between computer science and mathematicians where mathematicians say that the natural numbers start at 1, and computer scientists say it starts at 0, and then argument ensues, and you can define it in different ways, but depending on how you define it, that might change some definitions later on. So it's not that you can only use the definitions I'm giving you, it's more that you can't use something until you've defined it and made sure that you're allowed to define it that way. So to make this, since this is more of an introductory class, I'm not going to expect any of you to make up definitions. We can certainly talk about what would happen if we define something a different way, but certainly the definitions I give you are all that you're allowed to know, right? And for example, when you're proving, and I'll talk about this later in the actual proof section in a few days, but this comes down to the whole idea of I can't prove things just by saying, oh, this makes sense, or this is what I'm used to doing. You have to be able to justify each step. And logic is one of the ways we do so. As an overview, so I'm going to keep going on logic, but today we're going to talk about propositional logic and predicate logic. I'm not going to go really deep into proofs from a logic standpoint because it's a bit different. When we talk about proofs in math, we're just like writing out some paragraph or writing some equations that will show, why a theorem is true or something like that. Proper proofs from a logic standpoint get really formulaic. There's like specific ways in which you write proofs. There's specific ways in which you use things like, all those terms you'll hear in court, like modus ponens, avoiding a fallacy or fallacies and stuff like that. You actually do end up using them in logic, and you do end up using that to prove things step by step. But we're not going to go that deep into it. We're just going to kind of use logic to get this idea of how we can build up mathematical objects, mathematical statements, and get what we get. So this is like one of the first lessons I always teach in mathematics is it seems stupid to be talking about statements, right? It seems stupid to be talking about something so easy, but at the same time, it tells you that even with stuff that's so easy, there is a lot of depth to it, and there is stuff you have to kind of think about. And speaking of mathematical objects, I always joke that when I teach, there's a few words I ban and don't allow people to use, and that's one of those words. Don't use that word this fast. And what I mean by that isn't just, don't use the word it. It's more like a lot of people when they ask questions in a class, they'll use, oh, I think I got that. Does it imply that blah blah blah? Or they'll use the word it to refer to something. Pronouns in our class can get really hairy because it becomes this whole dance of like, I don't know if you know what you're asking, or I don't know what you're referring to. It's more than just I don't know what you're referring to. It's I don't know if you know what you're referring to sometimes. And so I want students, when they're learning this stuff, to be really careful with knowing what exactly they're talking about, right? So instead of saying it, refer to the actual thing, refer to the object. And this also gives you a practice in, naming the object. It's, if I point at it, I might be pointing at an equation or a formula or a statement or something like that, but those all have different meanings, right? So practicing and getting the habit of talking about objects in terms of how you're naming those objects can be really important. And that's what I want to kind of help people with this, by not letting you guys use that word, or by kind of helping you guys get rid of that word in your mental vocabulary. This means that when you're reading or when you're writing your own stuff in math, you start having this idea of, okay, let me actually figure out what this object is, right?
So JJ, you said that x plus 7 equals 9 is not a statement.
Correct, it is not a statement.
The reason it's not a statement is because x, we don't know what x is, or we don't know what class does x belong to.
Both.
Is it a number or is it just a squiggle?
It's both. We don't know anything about it. Oh. Right. So for example, 7, we know what it is. I haven't told you guys how to get 7, but there's a way to get it.
So it's like someone has only learned 2 numbers, 7
exactly.
and 9.
Yeah.
Knows nothing.
Let's say you know what 7 and 9 is, right? Maybe you even know what plus means. Maybe you know what equals means, right? But you might not know what x is. Does that make sense? Right. So like you said, not only do you need to know what the object is, you also need to know how you get that thing.
So we don't know what x is. Does that mean we don't know what the value of x is, or we don't know what x is?
The second one, right? We don't know what it is, right? It might even be just a letter, right? We could say, now, if I told you this was the letter x, right? I can say the letter x plus the number 9 equals, plus the number 7 equals 9. Now that would be a statement. Even though it doesn't make sense to add apples and oranges, I'm still telling you to add apples and oranges, right? If I tell you, hey, apple plus orange equals pear, it makes no sense, but that's still a statement. I might be doing things with these operations that I'm not allowed to do, but that's still a statement. There's a little bit of, how do I want to say this? Not conditions, but there's a little bit of nuance here just because it also depends on operations, which we haven't talked about yet. But for those of you like, we know what plus is, right? But technically, plus is a specific thing. It takes 2 numbers and adds them together in some way. But that means as an operator, that's just a function, right? So some of you who've seen algebra before might recognize plus is a function that takes maybe 2 real numbers and spits out a real number, right? And again, so I'm doing this more of an example, but you can imagine that I haven't defined the word function yet. You guys maybe don't know what a function is, but for now, let's go back to the world where we live and you know what a function is. It takes in things and it spits out something else. But when I say it takes in things, I have to tell you what the machine is allowed to take in, right? So maybe sometimes you can say that, well, even if all this stuff is defined, if you define x as a letter, plus is a function that takes two real numbers and splits on a real number, a letter isn't a real number, and so we can't do this. So in that case, it wouldn't be a statement. So so like I said, this is why there's so much depth to it, right? There's a lot of reasons why something might look like a statement, but isn't a statement, no matter how well you define it. And really, this just tells you, well, what's the easiest way to get around this? Just define everything really well, right? So if I'm really confused about what's a statement and what's not a statement, let's just be really specific and make everything into a statement. That's kind of the idea, right? This is another way of saying just don't write down nonsense, right? The easier the more you make it clear to yourself what you're writing down, the easier it is for you to decipher what's actually going on. Let's go back and make sure I open a chat up for the Zoom, just in case I get that. Okay, so we talked about statements, but if that's all we have, well, we obviously need to do more than just statements to talk about things, right? So we need to be able to combine statements in some way. We need to do multiple statements. So I mentioned molecular statements, right? You can think of the exact like chemical or physical like application. I call them atoms and molecules. How do I combine atoms to make a molecule? Well, in chemistry, we call them bonds, but in reality, conceptually, these are just connections, right? We're connecting atoms in some way to get molecules. So in other words, let's talk about logical connectors. So these are symbols that allow us to combine statements. And it might seem like there's a lot of ways to combine things, but in reality, there's only 5. There are only 5 logical connectives, and a lot of them are pretty similar to each other. So I already hinted at and gave one of the connectives when I said the moon is blue and brown. Well, I used the word and that's how I separated those, right? So that's this symbol, which some of you might have seen before. Formally, this is called a conjunction. When you ever hear the term conjunction, it's specifically referring to this connective. Informally or colloquially, this is really just and, right? So I can say this and something else, so on and so forth. You can think the opposite, there being a conjunction. Now this section, which we can think about as with or. Right. So if we have A or B, that would be this junction. Now, one very, very important note about the word or. English is a terrible language. English sucks. Because if I say something like, well, I want to go eat at Hawaii Poke or I want to go eat at Taco Bell, like, it doesn't mean I can go to both. It means I'm choosing one over the other, right? It's exclusive or. Whereas inclusive or means I can have both, right? So for example, when I say something like, hey, you either get a 70 on the test or you fail the class. I explicitly mean one or the other. You can't have, now I'm forbidding you from getting both, right? That's not the case in this or. This is inclusive or. Right? So in other words, the statement would be true if either A is true or B is true or A and B are both true. That's all allowed. And we'll go a bit into this when we talk about truth tables in a few minutes. But it's really important to note that we are specifically talking about inclusive or, especially for those of you who know some comp sci and know that there's a very big difference between XOR, which is exclusive or, and just regular or, right? So that's what we use here. The third is a negation. We'll use specifically the symbol. Informally, we can call this not, right? Basically, you can think of this as the opposite of something. So not A is false. If A is true, then not A is false, for example, right? So that's the negation. And then the last two are going to be pretty similar. A lot of books use a single arrow. I'm going to use a double arrow just because I think it's more mathematically like obvious what this means. But just know that in some books in logic, you'll see this denoted by a single arrow. Well, in other words, with a single line instead of two lines, but they both mean the same thing. So the single arrow, it could go both ways, right? It could go from left to right or right to left. It's really the same connected because I can just, instead of writing this, that's the same as writing this. It really doesn't matter, right? I can just move it however I want. That's still the same connected. So this is then called the conditional and the biconditional. There's a lot of ways to denote these informally. For conditional, the easiest way I tell people to think about it is if blank, then blank, right? So this A implies B with the arrow going from the A to B means if A, then B, right? Now biconditional, a lot of you have heard the term if and only if. Some of you might recognize if people write IFF in the math textbook, it's not because they have fat fingers and press the F twice. This means if and only if. You see two Fs. Another way you would hear it is necessary and sufficient. And I kind of get it, like I'll get it immediately confused. Sometimes it takes me a while to think of it, but it's a good exercise to say like, okay, if this is necessary and sufficient, that means probably that one direction is called the necessary condition, and the backwards direction is maybe the other direction is called the sufficient condition, right? One of them is necessary, one of them is sufficient. Try to think about which one is which. It's not as easy as it sounds, but you want to think about like, if I have A implies B, this is obviously if A, then B, or I can say B if A, and so on and so forth, right? So looking at the if and only if part, the if part, let's see. If I want to say A is B, this is the same as the statement B implies A, right? So the thing's going backwards, which tells you that if I'm talking about A only if B, well, what does only if mean? It means that if A is true, then B has to have been true, right? So A is true only if B is also true, right? So that's kind of how we think about how we use the grammar to get both sides of the statement. So you can try to think about the same thing for necessary and sufficient. And so when I said that English is a terrible language, I mean that it's sometimes hard to take English statements and translate them into the proper statements within propositional logic. And this is one of the things that you should do when you are learning math, right? This is something that when you read a statement, try your best to write it as a statement using symbols, right? That's kind of what we want to do. Now, I haven't given you a lot of symbols because propositional logic is a little bit cramped. It's a little bit, it's not really sufficient to talk about every single type of statement we can talk about, right? Because notice, the whole x plus 7 equals 9 thing, we don't have a way to talk about it yet. We don't know what a variable is. We don't know, we just know that we have statements, right? And obviously, there are things we can write down that are more than just statements, right? There's things we can write, like if I write 2 plus 3, that's not a statement. So within propositional logic, I'm only dealing with statements so far. If I write down If I write down the phrase 2 plus 3, I look at the board at everything in white and go, oh, I can't fit this in anywhere, so I can't talk about it here. And that's what we'll get to in a little bit. But this kind of gives you the background for how you should be thinking about piecing statements together and piecing logical connectors together. Okay, so any questions on all that? Yeah. So obviously, we talked about the 5 different connectives, right? That's really all we have. Anything else that you might be able to think of is always a combination of these 5. So let's see how we can put statements together. And the easiest way to do this is through what we call truth tables. Some of you might have seen that. It's sometimes considered a pretty elementary thing to construct, but this will give us a couple other definitions. And just for those of you who haven't seen truth tables yet, this will be a great introduction to it. Right. So we can talk about all the ways we can depict kind of pictorially how we see these statements, right? So for example, I can imagine that if A is true, maybe this is a circle, and everything in the circle is a world where A is true, right? And if I have A implies B, that means that in some way, if I'm in A, I'm also in B. So you can think about this as, we'll discuss these kind of pictures when we talk about set theory a bit more. Think about it more abstractly for now, but you kind of see the idea that the only way for A to imply B is that A has to be completely inside B, because I can't have something that looks like that. Because if I have a statement here where A is true, it's not living in a world where B is true. So that picture kind of fails, right? We'll formalize this idea a little bit more once we've done more set theory. But for now, you can kind of think about, okay, what's going on here.
So if, maybe I'm jumping.
Go ahead.
So if we have a if and only statement between A and B, will that be the same word?
Yes, exactly, right? Now, we don't, when you use the word same, this is where we want to be really careful, because up to now, we haven't defined what it means to be equal. We don't even know what these worlds are, right? So if I want to say a number is equal to a number, that's different from saying a set is equal to a set, or the statement is equal to the statement, right? So that brings up a really good point. If I say A if and only if B, right? You're right. These two statements, essentially, in some way, they mean the same thing. But does that mean that A equals B? And it's not an easy question to answer. Again, it depends on what you mean by equal. I can design a world where I say two things are equal if they are logically equivalent in some way. We'll talk about what that means in a little bit. But it's a very hard question to answer without formally defining what it means to be equal. So that's a good question. You have the right idea. If A, if and only if B, then they have to be, if I draw the circles, they have to be the same circle on the board geometrically. But we have to be careful with using the word same. Does that answer your question?
Yeah, thank you.
Yeah. So the easiest way to do this is look at what we call truth tables. And the reason we can construct truth tables here is because we've already said that we're going to live in a world where if I give you a statement, the statement can either be true or false and nothing in between. Now, for those of you who've seen a bit more mathematics and have done some set theory, you will realize that what I just said is not quite true. There are some worlds that we can live in where statements can be neither true nor false. We're not going to live in that world right now because that world is really fucking complicated. We're just going to ignore it. There are cases in which you can think about that, but for our cases, for 99% of mathematicians and mathematics in general, we can just live in a world where statements are true and false. So I guess before I go on, I'm going to define this word. Right? Yeah, maybe I should have done this before. This isn't really like part of the logic thing, but it's something we should know, and I'm going to use this word a lot. An axiom is a statement that we are taking as fact. Or in other words, is true. right? There's no way for me to prove why it's true or why it's not true. An axiom is literally, hey, I'm telling you it's true. Let's build off of this. So what I just said can be reinterpreted as, hey, I have an axiom that I'm invoking, and this axiom says that all statements are either true or false, right? So maybe axiom 1, all statements are either true or false. And there's a subtlety here. A lot of people ask me whether axioms and definitions are technically different things. They're not, right? Because when I define something, I'm telling you what to use it for, right? I'm defining what it means. That's essentially what an axiom does. So you'll notice I wrote this out just to be clear, but I technically already told you this, right? Previously, when I defined a statement for you, what I wrote out on the board is I said that a statement is something that we can write out and can stand alone that is either true or false. This axiom is part of what I said there, right? This axiom essentially built into the definition I gave you, right? But I just want to write it out again just so we're clear. This is an axiom, right? This is not true a priori. And by a priori, I mean without having said anything else, right? Like we can live in a world where I give you axiom 1 as saying all statements can be either true or false or somewhere in between, right? But like I said earlier, when I change the definition, I have to change math.
But this axiom cannot be true or false. It is true.
Yes, exactly. Axioms are just statements that are true. And so we just take this.
Otherwise, it's worse.
Exactly, right? If you want to go further, there's this thing called like Gödel's incompleteness theorem that says that any world of law, so like you can think of the world as like built up on statements that are facts, right? Are true or not true. It's been proven that it's impossible to have a world where there's 0 statements that are axioms. You always have to have some statement that you just take as true, right? And to prove that statement, the only way to prove an axiom is by going outside the world, right? And so back in the late 1930s and 1940s, this is actually where a lot of propositional and predicate logic came out, is Gödel was using kind of these arguments like arguments called like religion argument and stuff like that. There was a lot of things that came out of math because of religious arguments on what's allowed or not allowed. You know, there's a lot of these people who try to prove that God existed or prove God didn't exist using mathematics. And this is actually where a lot of this came out of. A lot of the formalizations to set theory and propositional set theory and propositional logic came out because of religion debates. So welcome to math. A lot of stupid stuff happens, we get useful things. But yeah, so the idea is that I'm going to be using this word a lot, and whenever I say something's an axiom, it really means just that, hey, I'm the law, I'm telling you this is true, don't fight me on it because I'm not going to fight back. I'm just going to tell you, believe it or get out, right? That's essentially what an axiom is. So we take as an axiom that all statements are either true or false, which means that now, so a truth table, consider all the possibilities for statements being true or false and sees what happens, right? And then we can do some sort of computation. And so I talked about, you know, a formal and informal way of talking about each of the 5 connectives, but you will notice I didn't quite define them, right? I told you how they work. I told you informally what word in English we can use to say how they work. And I've even told you the words you use to describe them. I told you this little weird wedge symbol is called conjunction, right? And you know what that means in your head, but we don't have a definition for it. A truth table is the easiest way to define what this means. So a truth table looks something like this. So let P and Q, these statements. You'll see a lot of books use A and B for statement because obviously A and B are the first 2 letters of the language. If you're curious, P and Q just because P stands for proposition and then Q is the next letter. So a lot of math books will use P and Q. So if I want to list out all the possible ways in which P and Q can be true, well, let's just start with P being true, right? Then Q can be either true or false. And now we change P to be false, and then Q can be true or false. This is not too hard to see. Now, how many options are there here? There's 4 options, right? One of the ways we can think of this is, if I want to see how many options there should be in my table, I can take to the n, where n is the number of statements I have, right? And the reason we have this is, let's say I have statements A, B, C, D, blah, 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 right? Let's say I have n statements. There's 2 options for A. They can be either true or false. There's 2 options for B. B can be either true or false. 2 options for C, and so on. So since each of these have 2 options assigned, I'll just multiply all the 2's together to see how many statements there, right? So that's why it's 2 to the n. So you can always check yourself. If you drew out the table and you're not sure you covered all the possibilities here, just do 2 to the power of however many statements you have, right? This is similar to the kind of idea that you get the stupid math questions that are like, hey, if I have 3 different colored shirts and 3 different colored shorts, how many ways are there to combine them? It's just 3 times 3 is 9. That's that same idea there. So that's just a quick way to see that. But here what we're doing here is we want to define all the operations, right? So the first logical connective is the and or the conjunction. And we said that's true only if P is true and Q is true. So in this first case, this would be true, but this is false in every other case. And maybe this will be helpful. Maybe what I'll do is make this a bit clearer. Okay, I cannot see that. We talked about the disjunction. This one's obviously true, right? This one's true. This one's true. This one's false. Right. So this is where we note that this is inclusive OR, where we include this first case. For computer scientists out there, if you're doing exclusive OR, it's the same truth table except this first guy is false. And by the way, this is maybe bad notation. I should really write this out. When I say and, I really do mean P and Q. For or, I mean P or Q, right? But basically, you're just treating these connectives as putting 2 things together. I'm going to skip the third one because I have 2 things here, right? And you can see that the third connective, the negation, only cares about 1 thing, right? Another thing you can think about, we call them binary connectives and unary connectives, right? There's only 1 unary connective, and that's the negation. It only needs 1 thing, right? I don't negate PQ without putting anything else in, right? Before I do something to 2 statements, I have to use one of these 4 connectives. So let's think about this a little bit more then. What does P implies Q mean? Well, sometimes this gets a bit hard to think about because we might say, okay, if I have P implies Q, that means if P is true, then Q is also true, right? So immediately we know how to fill this in. If P is true, right, and Q is also true, this is fine. If P is true and Q is false, that can't be true. However, let's look at this. So my statement was if P, then Q. If P turned out to be false, does that technically fight against what I said? It doesn't, right? Because all I said was if P is true, then Q is true. But if P turns out to be false, what that means is it doesn't matter. So if I say a really stupid statement like, if I have 5 legs, then the queen is male, that's a true statement. So these are called what we call vacuous truths. Vacuous meaning that I say here that I need P to be true for this to be something else. But if P is not true, then we don't care, right? The truth value of the statement depends only on what happens if P is true, which means that if P is false, then we don't care. This statement's just vacuously true because it's nonsense in the first place, because you can almost think of it as it's not wrong, right? I can say something completely nonsense, and if I haven't defined anything, I'm technically not wrong, right? When I'm wrong is when I've defined everything, and now that everything has a definition, you can tell me how I'm wrong. You can almost think of it as like, you can't prove me wrong unless I've told you what the words I'm saying mean, right? It's one of those, you guys, I'm sure you guys have seen the stupid online arguments where people argue over semantics and they're like, oh, you're wrong because this word means this. And they go, oh, no, you're wrong because this word should mean this instead. Well, in our language, they're both right because they haven't properly defined what that word means, right? Everything is based on definitions. And so here, when our definition says that we have P implies Q, meaning that if P then Q, by not having P being true, by having it be false, we can't say anything about a statement being wrong, and therefore the statement is true. Right? This is one of the nuances in propositional logic that a lot of people don't see at first, but you kind of get used to it after a while. Does that make sense?
So P implies Q cannot mean if P is false, then Q is false.
It can, right? This is true. So for example, if I say the word, if I have 5 legs, then the queen is a dude. Those are both obviously false statements, right? But the statement P implies Q would still be true. Because the statement says that if P is true, then Q must also be true. So if I said something like, if I'm a guy, then the moon is red all the time. That would be false, right? Because I am a guy. So if I am a guy, for the statement to be true, the moon also has to be red at all times. Right? Does that sort of make sense? This is the confusing part for most people because it kind of makes no sense to talk, why do we care if P is false? Right? And that's really the whole point of talking about this guy. Right? Is when we want to prove something, if my statement has some nonsense statement implies something else, then it's always going to be true. But it also doesn't matter whether it's true or not because my first statement is nonsense. It doesn't tell me anything.
But you cannot read it as if P is false, then Q is false. Right?
Correct. Yeah, you can't read it that way.
Because then the first two will be wrong.
Correct. Mm-hmm. Yeah. And this is why we use truth tables, because now we can talk about, later we can talk about, we'll actually use that example. If P is false, then Q is false, we'll see what happens there, right? We can see what happens with that truth table. So finally, there's one more connective here. P if and only if Q. Well, this one should be a bit more obvious. There's 2 ways you can look at this. P, and maybe I should say this. Maybe I didn't say this earlier. When I have the double arrow, it's really the exact same thing. And when I say same, I don't mean they're equivalent. I mean by definition, these are the same. We define this as putting a bunch of other connectors together. I mean, it makes sense, but we have to still define it in some way, right? So when I have this guy, well, obviously I have this guy, but I need the other way. And you can imagine the other way would have true, true, false, true. And the only times in which those two agree are the first and the last row, right? So P if and only if Q is a lot easier to think about, right? If I have statement P if and only if statement Q, then either they're both true or they're both false, right? That should be a lot easier to think about. So these are all definitions for those 4 connectives. And I don't think I need to, but I'll write it out anyway. Well, P can be true or false. So in this case, not P is just the opposites, right? If P is true, then not P is false. If P is false, then not P is true. That should be fairly obvious, right? So here's all the definitions that we have for our connectives. Well, these are just definitions, right? Why do we use truth table? Am I only using truth tables to define things? So the answer is no. I could easily find a different way to define all these statements without truth tables, but the reason we use truth tables is that it makes it much, much easier to then talk about comparing statements, right? So maybe on the homework, I might give out a couple of examples of like constructing a truth table. And maybe here's a good like if we get something really complicated, like something like this, right? If you try to think about it in words, it can get really complicated pretty fast, right? If I want you to rewrite the statement using another statement without arrows, maybe this becomes pretty hard. But with truth tables, it's not that bad, right? So as an example for practice, let's look at what this would be, right? We have 3 statements. So 2 to the power of 3 is 8. So I should expect to have 8 lines. And maybe I have shot myself in the foot and I should write this a little bit higher and give myself some space. So I have P, Q, R.
What is the meaning of single arrow?
Oh, sorry. Yeah. Bad habits.
So they're both the same.
Yeah, so the idea is like the technical difference is when we're talking about logic, right? They use single arrows. But when we start doing math, when we're comparing math statements are different from propositional statements in some way. So they use double arrows. So sometimes people will distinguish them. And a single arrow you will use when you're talking only about logic and truth tables, and you use double arrows when you're talking about actual mathematical statements. But so like the reason I told you guys to just use a double arrow is like it just makes it easier to think about because they are the same thing, they mean the same thing. That was just me being used to like whenever I write logic, I just use single arrows. But like we should just stick with double arrows for now. Yeah, next. And so maybe here you guys can see how I'm organizing this, right? I just let everything be true or false, and then I go down the table. I still left myself barely enough room, but it should be fine. Yeah, fine, just keep myself tidy. So as we normally do, the easiest way to start looking at things is let's break it up into digestible chunks. Let's look at everything step by step, right? So if you look at P and Q, our definition tells us that P and Q is only true when both P and Q are true and false everywhere else. So I don't need to look at R. I just need to look at P and Q, right? So here's true. Is true, but all the rest of them are false. So maybe I can use this. Now, the other connective I have is this implies R. I'm going to write it like this and have the whole statement. But another way you can see it is imagine we just call this column B, right? Now that I already have truth values for this column, I don't need to call it P and Q. I can just rename it, right? I can say the statement B is defined as a statement P and Q, right? And so I can name this column B, and then this would just be B implies R. And so now I know how to combine these two connectives, right? Because I have a table over here that by definition tells me how to put these together, right? So one thing you might be able to do is maybe you, just for convenience, before writing this out, you might take R and copy it over here, just so it's easier to do that. If you want to do that on your own, that's totally fine. I'm not going to do that because I'm lazy and I don't want to write out another column, but you can easily see like how you can do that. So if we look at P implies Q, this is, the way I like to think of it is this is only false when the first guy is true and the second guy is false. Any other time, this will be true. And maybe instead of always using the words first guy and second guy, I'll maybe give a definition, right? Whenever we have an implication, we call P the hypothesis, and we call Q the conclusion, right? Which I'm sure you guys have all seen in science, right? You know, you have a hypothesis, that leads to a conclusion. It's kind of the if-then statement thing. We use that same terminology here in logic, right? So P implies Q as a statement is only false as a connective if the hypothesis is true and the conclusion is false. So here our hypothesis is B, this column, and our conclusion is this column. So let me just go ahead and mark out all the columns, or I guess all the rows, where the hypothesis is true and the conclusion is false. Well, makes it easy because I only need to look at this. In all of these, the hypothesis is false, so I don't care about this. Here, the hypothesis is true and the conclusion is false, so this is false. But in all other cases, I'm perfectly fine. So this is the idea of constructing truth tables. Once I have a definition for each of these guys, it makes it a lot easier for me to see how we can put them together to say, okay, what is the truth value of this? When is this statement true? This tells me this statement is the same as, is only false when P is true, Q is true, and R is false. Let's see how to write that. So we talked about using and not, right? Not is the same as negating something, and is the same as just looking at them one by one. So how can I say this in words? I can say that this statement is false if P is true and Q is true and R is false, right? So there's a lot of intonations I'm doing there just because I want to make clear that we can just treat this as connectives. So I can rewrite this statement as P and Q and not R, but that's when it's false, right? So I would take the negation of this whole thing. Right, so that's another way you can rewrite statements by breaking them down, writing it out as a truth table, and taking all the parts where it's true. Right? That's one of the ways I can do this. So now you might say, hey, if I'm doing stuff with parentheses and I'm trying to flip everything, am I going to have to go through this every time to write that out? And the answer is, well, if you want to be sure, yes. But obviously, like in anything else, there are shortcuts we can take, and there's very common things. Right, so one thing you will see in logic a lot is what I call the Morgan's laws. I think you guys are good with this, so I'm going to get rid of this table. Actually, I'll leave these two up. It's obvious what and or, but I'll leave these two up in case we need it. But with these things called the Morgan's laws. I won't prove it. I might leave that as an exercise for you guys to prove. Maybe on the homework, I'll let you guys prove the Morgan's laws using truth tables.
Is there a not before the bracket?
Here?
Yeah.
Yes. Because the reason why there's not is because this is false. Right? The thing inside the bracket is the line that I'm picking out, but that's the case where this is false. So I want everything else. I'm gonna keep writing what I'm writing. I forgot to define a couple of things. I'll go ahead and define it after this, but for now, just imagine you know what equivalent means, and I'll talk about it in a little bit. So essentially, the Morgan's laws are a way for you to distribute, in very big quotation marks, distribute a negation over conjunction or disjunction. And this squiggle just means is equivalent to. And I'm basically just flipping everything on the inside. So let's think about this logically, right? What does this mean? So if I say that, let's see, how do I say this? If I say the statement, the moon is both blue and round, right? What would it take for that statement to be false. It doesn't have to be not blue and not round, right? Only one of those things has to be false. So if it's either not blue or not round, that immediately makes the statement false. It's this guy, right? Notice that we don't just have to negate these two things that we distribute to, we also have to negate this conjunction or disjunction, right? We change ands to ors or ors to ands, right? So that's called the Morgan's loss. So on the homework, I'll probably put one of these guys on there, and it's quick to prove that they're logically equivalent. So this brings me back to the point, what the hell does logically equivalent? It makes sense, and maybe you have an idea of what it should mean, but let's define it, right? No matter how intuitive you think an idea is, and no matter how like obvious it is, you always have to have a definition before you can begin to talk about it, right? So two statements are called logically equivalents. And there's a lot of ways to define this, but in our setting, the way we've defined everything is using truth tables. So I'm going to continue using truth tables here. The two statements are logically equivalent if they share the same truth table. In other words, I'll draw the truth table and I'll have a different column for each of these two statements. And the two statements are logically equivalent if you read down the rows and every single one matches up with each other, right? So what would it mean to prove this first statement? It means I will write out a truth table with P and Q. I'll see what this guy looks like, and I'll see what this other guy looks like. And I want to show that the truth tables look exactly the same. Now, this goes back to what Mama was asking earlier. Do you have some sense of it being that these are the same, right? So this is where we use the word logically equivalent instead of same. Because same could mean a lot of things. In this particular setting, if you want to compare two different statements, we use the term logical equivalence. And here's why I say that we're talking about this. This is a statement in and of itself, right? It doesn't necessarily mean that A and B are logically equivalent, right? Maybe they do, maybe they don't. You have to prove that. It doesn't mean by definition that they're logically equivalent, because you have to do more work to show that they have the same truth table. It turns out they do, right? If you look at the definition, you'll see that they have the same truth table because if you write P and Q down, right? P has its own truth table, Q has its own truth table. These are the cases where they have the same truth table, right? So that's how you would have to look at that. But this kind of induces another definition that we need. Let's do another example. And this example maybe is a bit longer, so I won't go through it slowly. I'll just write it out as is. And if you want, you can try this on your own, or feel free to ask me if you're not clear on one of the shortcuts. So I'm basically going to use a bunch of shortcuts to solve this. But essentially, imagine you're trying to find a truth table to this statement, right? So again, I'll do the same thing. And let's see, there should be one more. Okay, so we've got immediately two statements. Q implies Q, and Q implies R. So this is only false when P is true and Q is false. So it's false here and true everywhere else. And Q implies R is only false when Q is true and R is false. That's here and here. So notice something. What's about to happen when I use the OR? Or means that the only time it's false is if both of them are false, right? But look at both of these columns. In every single row, at least one of them is true, right? There's not going to be any row where they're both false. So if this is my statement that I put in here, what's every row going to look like? It's all going to be true, right? It's almost like saying, hey, the sky is blue. It's like, I don't need to tell you that. You know the sky is blue. It's all, no matter what implications I do, this statement is always true, no matter what I plug in for Q, R, and P, right? Then there's a common saying out there that like, oh, here's a trick. If you know, maybe you're teaching a whole class on like propositional logic, I can give you a question that's like saying, hey, if you're playing Monopoly, is it true that the statement that either you'll roll more doubles, and if you roll more doubles, then you will lose the game, or if you buy more properties, then you will lose the game, or something like that, right? Obviously, most kids are going to sit there and go, oh, crap, I need to know what Monopoly rules are to try to figure out what the statement means. But this says it doesn't matter. I can put anything I want into P, Q, and R, and this is always true. So we call this tautology. The statement is a tautology if it's always true, right? So if I just have so maybe here's an idea: an atomic statement can never be a tautology, because an atomic statement is allowed to be true or false, right? When I write out just P by itself, P is allowed to be both true and false, right? So a statement, just a pure atomic statement by itself, can never be a tautology. But when I put enough things together where the end result is always true, that's when I get a tautology. Right. So maybe a good proposition here is that if A and B are statements, sorry, I'll just say if A and B are logically equivalent. In other words, if A and B fit this statement up here, then this statement is a tautology. Right? Because if A and B are logically equivalent, that means either they're both true and they're both false. So when I write out the truth table for A if and only if B, that thing is going to always be true. Right? And that's what we call a tautology. So one of the things that people mess up a lot here is, again, objects, right? So logical equivalence is an idea that talks about two different statements, whereas a tautology is talking about a single statement. They obviously have the same kind of idea, right? There's this whole idea of like, oh, there's this idea of always true behind logical equivalence. Logical equivalence means two statements are the same in some way, and tautology means that, oh, this statement's always true. So they kind of have the same meaning embedded into it, but we use the two words differently depending on what situation we're talking about. If we're talking about comparing statements, I can't say, oh, A and B are tautologies with respect to each other. That makes no sense. I mean that A and B are logically equivalent. If I want to say something's a tautology, I would say A if and only if B is a tautology, given that A and B are already logically equivalent. Right. Here's the way we can see this. In words, it makes sense that this is something we should think about. If we write it out, it becomes really dumb. Because this is an if-then statement, right? So really, this becomes that's a really obvious dumb thing to write, right? Of course, this is always true. Of course, this is a topology. But this statement is embedded into something that doesn't look as dumb, right? So this is why we use truth tables, and this is why we use propositional logic. It's a way in which we can parse out statements in a way that might make more sense, where if we just try to write it down as is, you get something stupid like that. That's obviously true or obviously false. It makes it easier to think about it once you actually write it out. So So in summary, every single statement can be written as some combination using logical connectors. And the moral of the story is every single statement has a true and false values. We can combine statements using logical connectors to make other statements. So no matter, as long as something has a true and false value, I can figure out exactly when using a truth table. So truth tables are how we define this. So that's propositional logic. So this basically finishes the section I wanted to cover on propositional logic. So any questions on that? I'll give a couple.
So you said that if you spell it out in English, it makes more sense?
Usually it's the other way, right? If I give you something in English, you should always spell it out in math, right? And when you write it out in math, now the whole point is it doesn't matter whether or not it makes sense, because now you can draw a truth table, right? The idea being that if I just say a bunch of words and you're trying to figure out if my statement is true or not, right? Just let's put it this way, right? It's one of those stupid like IQ questions that is like, oh, if Mary is standing in front of Bob and Bob is the fourth place in line and this and that and this, then is this statement true? You're gonna go crazy trying to figure out everything if there's a lot of stuff. But if you treat each of them mathematically, now it doesn't matter because now I have definitions. I could tell, once I write down what all these statements represent, I could just tell a computer to do it for me. The computer doesn't know how to think critically like we do.
So that problem can be solved using logic.
Exactly.
It doesn't matter how many steps somebody is behind someone.
Exactly. We can write these as statements. We can write it in some way. And if we write this in some way, we give everything a true and false. We can easily solve it. Might take more steps.
That will be a good homework problem.
Yeah. Exactly. And this is part of what math is. It's even when you get into research level mathematics and you get all these, really hard statements to prove, and you get these things that are, you don't know what to work with, you always want to break it down into what you're actually trying to show. So a lot of times you want to actually just forget what you're actually talking about, right? If I have a really big statement that if blah, 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 and if you like 5 conditions, if A, B, C, D, E are true, then F has to be true, right? If I said some really long mathematical thing, if you sit down and just try to prove it straight up, you might run into some issues, right? You take a step back and go, okay, you know what? Let me just write this out. A, B, C, D, E are true. This gives me some things I know. I know this is true. I want to show using these things that F is true, right? In other words, I'm breaking them down into statements and using that to kind of think about what structure do I need to prove something is true. And obviously this gets more and more complicated as you do more stuff and you learn more math, but it boils down to the same idea. When you want to prove something, if it's a statement, I can write it in some format like this.
Is there a transformation? Is there a way to directly go from one logically connected statement to another?
Yes, exactly, and that's the idea of
to express it.
That's the idea of proofs, right? Everything. So remember when I said that like there's a way to like write things down as proofs, and I also told you that like I could give you a statement like if f is a continuous and differentiable function, then the mean value theorem holds or something like that, right? I can take that statement in English, turn it into a bunch of statements, and then within logic, there is a way to write these statements down in a way that you can prove them by maybe showing the truth tables are the same, or maybe showing that you can go through a bunch of logic and say, okay, what does this mean, right, and so on and so forth.
What I meant was, can we avoid truth tables?
Oh yeah, absolutely.
Like in representation theory, we have it for matrices. We can go from one representation. I mean, within a representation, you can prove something starting from somewhere.
Yes, that's exactly. Yeah, you can do exactly that. It takes a little bit more formulation to go through that. It turns out you don't really need it a lot of the time, but you can do that, right? So one of the ideas is another representation is using stuff like notice put. So for example, if I write a statement like either P or not Q and Q, let's say these two statements are true. What does that tell me? That tells me that P has to be true. Now, it's not immediately obvious by using the truth table. It looks like I have a lot of stuff to write out, right? But the idea is that, well, this tells me that at least one of them has to be true. But if Q is true, then not Q is false. So it can't be this guy, so it has to be the other guy. Right? Obviously, this is called the law of cancellation. So there's a representation going from truth tables to a representation using a bunch of different laws and axioms. You've got like law of modus ponens, law of cancellation, law of conjunctive disorder, and stuff like that. There's a lot of ways to put it together in the exact same way that truth tables do. If you want to be even more so, for those, I know there's maybe a couple of you who are watching these recordings who might have seen category theory before and have heard of it. Basically, you can talk about categories of not just mathematical objects, but also mathematical ideas. So you can talk about the category of propositional logic, and you can extend that to an over category, which is the category of maybe Boolean algebras, which is what you see here, right? This is all Boolean algebra. There's a representation, in other words, there's a functor from the category of Boolean algebra to the category of propositional logic, right? So that's the kind of representation. You can construct things out of these two things and link them in some way. And the functor tells me, okay, I'm doing something here, how do I do it in this other world, right? You can think of this categories as just worlds that you live in, right? I might live in a world where I might do math very differently than someone else. But if they're these two worlds and they should be the same thing, there's a way for someone to play the role of a translator and go back and forth between the two worlds and go, okay, if he's doing it this way, this is how you turn it back to this other way, exactly like you do in representation. Does that answer your question?
Yep, thank you.
Okay. So that's propositional logic. There's one problem with propositional logic, and I've mentioned this problem a couple of times. And the issue is that I haven't really talked about variables. And that's kind of a big problem, right? Like one of the big areas in math, not even areas in math, one of the big things we need to discuss is what if we don't know something? What if something's a variable? And so far, we haven't talked about any of that yet. And when I say that every mathematical statement can be written as something like what we've done so far, those of you who've heard me lecture on proofs before, and those of you who've seen me teach before, will notice that I'm missing something very big that I stress all the time. And that's because we need to now talk about predicate logic. So the idea is, what's a predicate? Now, a predicate is kind of, so informally, a predicate is the thing we use before we learn what a function is, right? It takes the place of a function while we are still talking about logic. So I could have a predicate, maybe label it something like this, where dot usually just means like some argument or some variable. I'll start using the word variable here. So when I use the word arguments, I really mean input, right? For those of you who aren't quite used to math, a lot of times when we say argument, we just mean what are the inputs, right? So if I have a function, if I have a two variable function that takes in x and y are my arguments. People like to use the word arguments instead of inputs. There's various reasons for this, but I won't really go into it. Here's something else that's different about predicate logic. When I write out something, it has to be true. What do I mean by this? So let's say I have a variable x, right? Again, we run into the same issue where we don't know what this variable is. Now, I told you that x is a variable. I'm going to define very loosely a variable as an argument of a predicate, right? We'll say that variables are arguments of predicates. They're the things that go into the predicate that I've already defined. So the way in which we define this is, first, we define a predicate as something that needs to take in some certain inputs, and whatever the inputs are, we'll call those variables if they are unknown. They could be constants, that's fine, but variables are what you put in if they're known, and once they're known, they're called constants. So a constant is actually defined after variable. A constant is known fixed value for a variable. Right, so we'll never call them fixed variables, we'll call them constants. But if I ever use the term fixed variable, it means the same thing. So how can we look at this? So maybe we can have a statement like this. Maybe P of X is, and usually if I write a colon, that means is the statement, right? So this can be read in English as P of X is the statement that X is odd, right? I can put anything I want in X, right? It doesn't have to be something to which the statement makes sense or not, right? Obviously, this implies that maybe I want X to be a number, right? I want to talk about whether a number is odd or not. But I could also say X is a word, right? I can say X is blue. That's still a constant. That's still a thing I can put in. Well, blue is odd. The statement doesn't make sense, so it's obviously false. Just like in propositional logic, our statements are still true or false. But now the issue is this guy. We now have to talk about variables. Now, you asked a good question. How do we know what the variable is? Do we know what the variable is? Blah, 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 right? There's a lot of stuff under that. And so now in predicate logic, we need to talk about something. We need to talk about the variable. And this is one of the most important things. This is probably the single most important thing I want you to get out of this unit, right? When we're talking about propositional logic or predicate logic, if you don't remember anything else about this entire section, the most important thing is to talk about quantifiers, right? And those of you who've done math before in any way or read math before in any way will have seen quantifiers. But also, even if you've never seen math before, you've seen quantifiers, you just don't know it. So let's talk about what they are first. We have two quantifiers.
Can I ask a quick question?
Yeah, of course.
So P of X is a statement
That says X is odd, yeah.
that says X is odd.
Mhm.
So is that a question? It's a question.
We don't know yet. So this is part of what we're going to define. We can, so right now, if I just wrote this on the board, it's not a question, it's a predicate. So my
But it's a
predicate,
statement.
yeah,
So if I say, I can say Px is true or false.
correct.
If
Yeah,
it's false, then X is
correct.
not odd.
Correct. Yeah. But when we write things, so what I'm about to get to is I haven't actually written anything out in predicate logic. I just told you what the pieces are. So you're completely correct. We actually don't know how to write it up as predicate logic yet. But this is why we need quantifiers. So this is for every, each, all different ways you can say this, right? These are all different translations of the same thing. This is what we call the universal quantifier. Right? Universal being everything, right? So when we use for all, we call this a universal quantifier, and that we are referring to everything. Everything possible to put in. Sorry, this says input. So think of arguments as just inputs to your function, right? It's just usually the difference is that if I just use the word input, it's almost like I can put anything I want in there, right? But usually arguments are limited to the things that I'm allowed to put in some sense. It makes more sense when we're talking about actual functions, but that's neither here nor there for now. This other quantifier is there exists. This is what we call the existential quantifier. And if you can't tell why it's called the existential quantifier, then maybe you should get on my class. But this really just, this exists, right? It's less philosophical than the universal quantifier. But the whole point is these are the only two quantifiers that exist, nothing else. Now, we talked about before in propositional logic that I needed to state an axiom, and this axiom states that, oh, statements are true or false nothing in between, I take that to be true and move on with this. That's not the case here. This is not an axiom. It's not just, oh, in this particular world, we have for all and there exists and there's nothing else. No, this is just in general, right? This is not axiomatized. For all and there exists are the only quantifiers. There is no other world that we live in, right? There exists no world where you get quantifiers besides these because they're exactly opposite each other. Why is this? This is because no matter what world you're in, you might not have a way to talk about objects, but the way in which you would formalize what it means to take every single element and the way in which you would take only at least one element, those will always be opposite concepts. Because what's the technical opposite of everything? It's nothing, right? So the only way to put these two together is, well, if it exists, either it exists or it doesn't exist, right? And if it doesn't exist, then that's the opposite of this. So you can never have anything in between this, no matter what world or topos you live in, because no matter what kind of weird logic you create, well, you can't break that. So what do I mean by that? Maybe I should write a quick example down. I'm gonna toss back to propositional logic real quick. There's one proposition or obvious, it's pretty obvious, so I shouldn't have to write it out, but it's a good example here. We've talked about what not P is. So if I negate not P, this should be the same or logically equivalent to just P, right? In the world that we live in this world where everything's either true or false, these two things are logically equivalent, right? Not P is the same as P, and P is the same as not P. Now, there's actually something really tricky here. This actually depends on that axiom. This depends on the axiom. Well, okay, I'm going to keep saying that axiom. I'm going to give it a name. It's called the law of excluded middle. Right, so the law of excluded middle is the axiom that says that every statement is true or false. That's what it's called. There are worlds where you don't have the law of excluded middle, and it turns out that, yeah, not P is P, but P is not the same as not P. It becomes really weird to think about, but we need those axioms to make sure these two are always the same, right? And I say this because even something as obvious as that could be false depending on what axiom you use. And that's why these are so strong, because these will never be different. It will always be this way.
So under the axiom of law of excluded middle, that's true.
Yes,
So
when you assume the law of excluded middle, these two are the same thing. If you don't assume this, there are things that can go wrong. This, however, is always defined as this. If I take the negation of a negation, it is always the original statement, no matter what, because that's how we define the negation, right? By acousticals. But there exist cases where P might not be the same as not P, right? They might end up being different. So in other words, the implication goes this way. So in our world, when we do have the law of excluded middle, we have this, right? But if we don't have the law of excluded middle, it's possible that this is true by definition, but this is not true for really weird reasons. Actually, in fact, since you're doing some physics, there are a lot of field theories in which this is not true. There's a lot of topological field theories within the world and topos where you don't assume the law of excluded middle. And so yeah, so you want to know the mathematical stuff, but thinking theoretically, there are a lot of these quantizations that allow for this to be false, even within stuff that you don't have. My point is, you don't have to live in a really, really weird, fantastic world for this to break. There are some worlds that a lot of people use in physics generally, where we don't look deeply into the mathematics behind it, but it turns out you get stuff where this is false. So it's not really as far-fetched as you might think. Okay, so sorry for that aside, but this is just, I just wanted to make that clear to kind of denote the importance of why do I stress quantifying so much. So I kind of jumped around saying that before with propositional logic, I always make sure to say every statement can be written using propositional logic. Every statement can be rewritten using symbols. Now I'm gonna upgrade that. I'm going to say every sentence, doesn't matter if it has to be a statement, right? Every sentence, anything you say can always be written using predicate logic, no matter what. But what does this mean? No, predicate logic depends on the quantifiers. Because earlier I said that, well, we can talk about P of X, we can define the predicate, but we haven't been able to write it down. Another weird thing about predicate logic is I would write statements like this. Now, this is my statement in predicate logic. What's the difference? The difference is that I can't just write P of X down by itself. Because when I'm writing in predicate logic, now, when I write this, I'm saying this is true. When I write this in words, what this says in words as a statement is that for every X, P of X is true. So when I'm working within predicate logic, well, this is true. I'm saying it's true because I'm pronouncing it as a statement. So in predicate logic, you can think of it as kind of, you're not asking a question, you're stating this as a statement. And what you're stating can be true or false. But notice that the statement always has to include the quantifier, because the quantifier is what tells you what the variable is. In other words, another reason this is so important is because the quantifier tells you what variables you're looking at. So on homework 1, the first exercise, even though it was just to practice LaTeX, the first exercise was define the quadratic equation or the quadratic formula using statements. And a lot of people will go ahead and write, oh, if this, then X equals right. I'll write down the actual quadratic formula. Well, here's a couple of steps, right? A lot of people, when they say, if you ask them what's a quadratic formula, they're just going to give you this. Well, that's wrong because that's just a formula. What do I do with it? What are A, B, C, and X? And then if I ask that, people will go, okay, well, this tells me how to solve a quadratic equation. And they'll say that it tells me how to solve ax squared plus bx plus c. But then I might ask them, well, that's not an equation, that's just a statement. And say, okay, I guess the equation is this equals 0. And I go, okay, what about that? And they get to this and they go, okay, that's a statement. And most of you would look at this and say, okay, this is fine for a definition. If this is true, then this is how you find X. Here's the problem. What are A, B, and C? I haven't quantified that. That's the problem. Right? So when we write inside this definition, this is what I mean by we can write everything using predicate logic, but this is also why I stress quantify so much. You can rewrite everything using quantifiers. If you are not able to write, if you write something out and you're not able to insert a quantifier in there, you're doing something wrong. Because there'll always be a quantifier. Because really, here the quantifier is for all A, B, and C, maybe they belong to the real numbers, right? There exists an X such that blah, 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 such that this equation holds true. Right, but notice that I can take this statement and turn it into quantifiers. If then statements will always have a hidden universal quantifier, right? Because the if part of it is really just, here's my conditions, right? So for every case in which the condition holds true, you kind of think of it that way.
Do we also have to specify the domain of X?
Yes, typically you will, right? So in other words, X and complex numbers, right? So, and in fact, if you want to be, for this specific case, if I want to be really nitpicky, there's always 2 of them. You always have 2 roots. There might be the same number, but there's always 2. Right, so.
But it's talking about all possible values of X, right?
No, so this is all possible values of A, B, and C. There exists means there's one value. So given that, so I'm going to write such that.
No, I thought like X can be all the values in that, like all the values that X can take has to be in the
yes,
complex.
right. So in other words, the way you think about this is for all A, B, and C taking any value of the real numbers, there exists X and Y from somewhere in the complex plane such that this equation is hold true. But you want to be very careful in where you say all of it. Because usually when you say the words all of it, you're implying the universal quantifier. And for more difficult arguments, people even I sometimes I get confused because I don't realize I'm using the wrong quantifier because the statements get so convoluted. So this is one of the big things that you have to make sure you get right. And like if you're having trouble with a proof, the first thing you want to do is look at your quantifiers. When we start looking at proof writing, I'll start talking about ways in which you're going to use the quantifiers to structure your proof. And I'm going to kind of preface this now. I'm not going to go into it because I'm going to leave proper proof writing for when we talk a bit more about other stuff. But those of you who know me for a while know that I love to use the phrase, please throw your brain out the window before coming to class. That's because if you try to view math, so a lot of people think math is hard because you have to be creative, you have to like think of the right solution. That's all garbage. That's not true at all. Math is about this stuff. Math is like you use logic. Logic isn't creative. You're told that all these things are true. You're told what to do. So when you're writing a proof, there's almost nothing you can do creatively, right? You're given a quantifier, so you have to respond to that in some way. And we won't talk about it yet, but you'll see it later. If I ask you to prove a statement, your first step isn't think about how to prove it. Your first step is let me write an outline for my proof based on what the question is asking. Right? It's almost like you're back in like middle school and they're like, hey, solve this problem, and they've already given you an outline, and all you have to do is fill in the blanks, and then it becomes really easy compared to actually solving it, right? That's what you're doing in proofs. You really should already have a lot of the proof written out, and you just have to fill in the blanks. And that's the idea.
There's still some level of creativity involved because you have to choose a particular representation that.
Yeah, exactly. So the creativity comes from. So when I say there's no creativity involved, I mean more that you don't have to think up a new idea. The creativity that is involved comes with learning how to take the language and turning it into something. But here's why maybe that's also not creativity, because we talk about representations between maybe categories and ideas, and we have functors, right? So maybe instead of being creative, I can learn how to take one thing and what do I do to turn this into another. And that becomes the same process, right? So the idea is that you can be creative in thinking about how to reword something, but once you learn it well enough, there is no creativity because there's always the exact same way you would translate from one word to another, right? Think of it this way. If I don't know a language really well, but I know it a little bit, I can be creative and use context clues to translate it into English. Maybe I won't know exactly what it's saying, but I can take a few words, figure out what it kind of means, and translate it pretty well by being creative. But what happens if I know that language really well? I don't need to be creative. I know what it means in English, right? So I can, if I know it, the better I know it, the better I'm able to translate it. And that's how you should kind of think of that creativity. There can be creativity involved in learning how to translate between languages, but at the end of the day, once you know it's super well, that's all it is. It's a straight translation, right? That's how you should think about proof. There shouldn't be any, until you get to like really, really high level stuff, there should never be an idea of, I need to come up with a really fancy way of doing this that no one has thought of before. That will pretty much never be the case. Even for stuff that's not proven, or actually, better case, even for a lot of stuff that hasn't been proven until the last 10 years, like for example, there's this like prime number conjecture about primitive sets that was proven by some like Oxford grad student like last week, and it's been unproven for hundreds of years. Well, obviously, no one's proven it yet, so obviously you have to be some sort of creative and smart to come up with a proof. But if you look at the proof, it really is just this kind of stuff. It really is just definitions. The creativity comes from learning how to piece those sentences together. The actual outline, everyone should be able to read without that creativity. So that's kind of what I mean and what I want everyone to think about when you're trying to prove stuff in mathematics, right? But the biggest thing is, whenever I'm writing every statement down, I have to be rewritten with quantifiers. Right. So a couple other things I want to talk about in predicate logic. What are some formulas? So now I'm going to use the word formulas. I'm not going to define it, but I'm going to give you some examples of what formulas are. So formulas can be stuff of the form this, right? Some quantifier followed by a predicate. And here, I'm going to introduce a new symbol. So if T1 T2 are formulas, say T1 equals T2 is, and so this is where I start defining some of those words, right? So if I put an equal sign, again, there's a lot of ways to define what equals means. We're not really going to go into that, but you can form some equation where you talk about T1 equals T2. I can combine formulas using logical connectives from propositional logic. These are exactly the ones we've seen already. These 5 things, right? I can combine formulas using these guys, and it's still a formula. Right? So that will remain a formula. Last condition is there's no other formulas. That's all. So in other words, the only, like when I say, so you can see that I wrote this as kind of like examples or propositions, and there's some of them I left undefined just because I don't want to go into like too deep, like the proper definition, but you guys kind of see what it is. But essentially the idea is we first classify as what kinds of things are formulas, what can we do with those formulas, but the whole idea is nothing else is a formula, right? When we talk about formulas, we mean like stuff without the equality. I only included this part in here to show you when we say all these are formulas, what do we mean by things that are not formulas? That would be an example, right? Of a statement that is not a formula, because this statement has an equality in it. So we start getting things like, so notice now that we've moved to predicate logic, our statements should be written as predicates. Now, there are cases where your predicate, so maybe I should say this. Sometimes we call it an nth order predicate. Is a predicate with n arguments. So in this case, this is the first order predicate because it has one argument. If I have a predicate that has 3 variables in it, that's a third order argument. We are allowed to have 0th order predicates. And what that means is the predicate doesn't actually take any input as a variable, right? It can take nothing in, right? So if I want to talk about this base statements, like we talked about in propositional logic, if I say the ball is round, that's a 0th order predicate. It still has to be a predicate, but it's a 0th order because I don't have a variable. If I say X is round, then that's a 2nd order predicate. Now, statements, like before, compound statements,
So P of X is a predicate.
Correct.
It takes an argument X.
Yes.
And you're saying that we can have a, what is this thing called? We can have a formula. No, we can have a 0 order.
Yes.
Predicate, 0 order formula.
Right.
Right.
Yes. That just means it has no variables.
But that would mean that it has no logical. Oh, n arguments. Okay.
Yeah. It's just
So
arguments.
this is first order. Oh.
Correct.
I confuse it with like n connected.
Oh, yes, exactly. Right. There is a slight difference there. And that's because we can have connectives between predicates, but you can also have connectives inside predicates. And that's a good segue. That's what I was going to talk about next is, you know, these predicates can just be statements from propositional logic. But we have statements like P and Q or R, right? Maybe I can say that the moon is round and purple, but not square, right? That's a statement, but I have a bunch of stuff in there. That can still be my predicate, right? I have a 3rd order predicate that has a bunch of connectives in it, and then I can still put connectives between them. right? So my predicates can still have arguments and have connectives in between them. Those are not the same as the connectives between predicates. No, that's all right. That's a good question though. But yeah, so that's how we talk about that. But again, the big difference is when we talk about statements, statements all have a true or false value. Well, this is still true when we talk about predicate logic, but the main idea is when we write out our formulas, the reason we need quantifiers is because when I write something down, I mean that this is true. So when I say this out in words, right? So for example, in propositional logic, if I just wrote P, right, there's no arguments here because it's still propositional, P would be, say, for example, a statement that the ball is round. And when I say that, I would just say the ball is round, right? It could be true, could be false, I just say that. However, here I would say that there exists an object X such that the X is round and X is square or something like that. But I will take this one step further. When I write this out specifically, this says there exists an X such that the statement that says X is round is true. And the statement that says X is square is true. Does that make sense? So when we say statements like this implies that there's a true and false. Whereas here, when I'm claiming the statement, I'm actually saying that I'm saying the statement, but it has to be true. Does that make sense? They no longer have, they still have a truth or false value, but that's because this entire thing is a statement, right? So whether or not this is true that's what I'm just saying this is true. Whether or not this is true is dependent on the truth of each of these, right? So that's kind of the little nitpick there, and that's the thing that allows us to combine all of this stuff. That's the thing that allows us to use quantifiers to tie everything together, right? And it's hard to get used to it. It took me a while to get used to this, but it really is, it makes it easier to take any statement you want and turn it into these kinds of things.
Yeah, it's pretty interesting. It's like you're forming a sentence.
Exactly.
Out of small blocks.
Yeah, it's like the kind of thing where it's like, you know, if I'm saying a sentence, right, and I'm talking to some like 7-year-old, and they don't understand what I said, I can keep making my sentence easier and easier without losing any of the information until I get to a point where they understand what I'm saying. How do I do that? By definitions, right? Maybe I'm using a big word. That big word has a definition that comprises of smaller words, and I can keep going. That's sort of what we're doing here. We want to keep breaking it down to the point where we are able to process it, right? And that's why it's so important to consider axioms, right? I always tell people that, you know, how good you are at math has nothing to do with how smart or dumb you are. It has everything to do with how stubborn you are. The reason I say this is because if I see a hard question and I don't know how to, you know, answer it, I just have to be stubborn. I have to be stubborn and keep asking myself, what is this? What is this? What is this? Sometimes I have to do this forever. I have to do it for a really long time. But if I'm stubborn enough to keep going until I get to axioms that are just obvious, now it becomes much easier for me to solve. And so what I tell a lot of people is, if you're having trouble with a math question in any way, it's not because you're dumb, it's because maybe you don't understand what the question is asking. You will always be able to break a question down to a point where you know what it's asking, and once you know what it's asking, you're set, right? That's the whole idea.
Just a heads up, I will not leave at 1:50.
Okay, that's fine. He's at 1:55. Oh shoot, it's already 1:42. Okay, well, I meant to stop at 1:50. So let's see. Okay, so maybe I'll talk about one more thing, and that'll be a good stopping point. Talk about formulas. Okay, so we have quantifiers. Now that we have a way to talk about our statements, here's another thing that makes it easier to talk about. Negations. And for those of you who've done some level of higher mathematics, this word probably gives you PTSD, but that's fine. So the idea is, from propositional logic, a negation is just taking the opposite of something, right? But now you saw, like, for example, you looked at De Morgan's laws and you saw that, oh, maybe taking a negation of a conjunction isn't as immediate as I think it is. It seems obvious in De Morgan's laws, but when I start adding more and more stuff, it starts getting complicated, right? And so, for example, here is, okay, so here's a good example. I'm gonna make the statement, every cow is brown. What's the negation?
Not every cow is not brown.
Isn't.
Yeah, so there's a lot of ways to look at this, right? And it's hard to look at it because when I say every cow is brown, so there's the two standard things that people first say is not every cow is not brown, and there's another person that would say, oh, no cows are brown. Both are wrong.
Yeah.
Here's why it's wrong. So suppose this is the opposite of this. That means suppose the negation of this statement is this statement. So I have a statement that says every cow is brown, and a statement that says no cow is brown. But what if we live in a world where some cows are brown and some cows are not brown? That means that both of these statements are false, but they're negations. And the law of excluded middle says that every statement has to be true or false. We've broken that. There's no in between, right? So that's the idea. That's why that's not a negation. So instead, the negation, you have to think about it this way. Here, I can write this using quantifiers. This is technically how I can write the statement. My cow is now my variable, right? For every cow, cow is brown. That's how we write this in terms of predicate logic. So now the question is, how do I negate things using predicate logic? So it's really easy. Every single statement will be a bunch of quantified variables followed by a single statement. So even if I have a statement that looks more complicated, like this or something like that, you will always have a sequence of quantifier, quantifier, quantifier. There will only ever be one statement at the end. And maybe it might be a compound statement, but when we write things in predicate logic as a formula, there will only ever be one statement. You will never have something that says this and then there exists Z in other statements. If that's the case, you would have been able to write it with everything in front. So the idea is, how do we negate it? Step one, flip every quantifier. What do I mean by this? These are kind of opposites, right? So when I say flip it, I mean use the other one. That's all. So when I flip a quantifier, when I negate a for all, it becomes that there exists. And if I negate that there exists, it becomes a for all. Right? And since I said there's only one statement at the end, there's only one thing left to work with, the statement. So we just negate the statement, as we do in propositional logic. Right. So here, the opposite of a for all is there exists. If my statement is cow is brown, the negation is the cow is not brown. So to negate the statement, I would say that there exists a cow such that that cow is not brown. Well, what does there exist mean? There's at least one. There's at least one cow that is not brown. And that's how we negate things. And the way to say this is take the statement, let P of X be the statement that says X is brown, right? So if we let X be all types of cows or whatever, the statement would become for all X. Grammatically, and when I write things down on paper, I always include commas, right? So I would say for all cows, comma, the cow is brown, like I did here. But when people actually write down predicate logic, they don't include commas. They just write things down in a bunch of commas, good with no comments, and it gets really confusing. But I include commas just to make it clear, but typically in the textbook, you won't see commas. So this is what that statement says. So when we negate this, this would be the negation, right? I flipped the quantifier and I negated the statement, and that was it. So the idea is now I don't need to think logically, well, maybe logically is the wrong word. I don't need to think creatively to try to figure out how to negate a statement. I don't need to be like, okay, what does it mean to be the opposite of every cow is brown? The opposite is that, okay, maybe I can say that no cow is brown would be wrong, but then if I say no cow is not right, I could go down this rabbit hole. But at the end of the day, the whole point is I can change that statement into quantifiers, into predicate logic. And once I change it into something I can write down as predicate logic, I have this exact formula for how to negate it. I flip all the quantifiers, I negate the statement at the end, and then I'm done. Right? So now if I give you any statement, you should be able to negate it without thinking of a different situation, but by doing the exact same thing every time. I give you a statement, you write it down as a quantifier, and then you negate it like this. And that's the idea. Right, so I think that's probably a good place to stop. So tomorrow, I'm going to there's a couple other things I want to talk about in predicate logic, but not too many. So tomorrow, I'll talk about predicate logic, and I'll start introducing not proofs, but some of the techniques we can apply to proofs. There's also one more thing I want to talk about with propositional logic, but we'll include that with the predicate logic stuff.
Most of this is the first time
Really?
I'm studying.
Okay, good.
And then truth tables.
Yeah, of course. Mhm.
Not to this.
That's good.
Not
Yeah,
this formally.
Yeah, I was scared that you'd be kind of bored today as well. Well, if there are no more questions, then I will see you all tomorrow at 11.